Alright, hello class. In this video we're going to be continuing our discussion about the gradient and specifically how it helps us solve max and min problems. So that was a big thing that the derivative helped us with back in Calculus 1 was optimization problems, right? So we are going to try and extend that to surfaces. Alright, so as I was saying, in Calculus 1, when you have, say, y equals f of x, you could take the derivative, right, set it equal to 0, and it would tell you, or it could tell you, where you would have maxes or mins, right? Because, say, wherever you had a horizontal tangent line, you could possibly have a max, you could possibly have a min, or you could have a situation where you had neither, right? So this here would be like a leveling off point. Usually this was like an inflection point. Okay, but the idea was that anywhere where the derivative was 0 gave us a place to look to see if it was a max or a min. These were critical points. Okay, we have a very similar idea in Calculus 3, except instead of looking at the derivative, we'll be looking at the gradient. Now you might wonder how that works exactly, right? Because the gradient tells us the direction of steepest ascent, and it helps us find directional derivatives. How exactly does it help us find critical points? Well, if you think about if you're at the top of a hill, right? If you're standing at the very top of a hill, the question here would be, well, what direction should we travel in to ascend, right? What is the direction? What is the direction of steepest ascent? Well, there is none, right? We could maybe find the direction of steepest descent, but for that to work, its opposite direction needs to be the direction of steepest ascent. So if we find a direction that gives us the steepest descent at the very top of a hill, the opposite direction isn't going to be the direction of steepest ascent. And if we're at the bottom of a bowl, right, standing here at the bottom of a bowl, we can pick any direction to ascend, but there would be no direction of steepest descent, right? So that's the other question is here at the bottom of a bowl, right? What is the direction of steepest descent? And it turns out there's none, right? Because every direction is a direction of ascent. Here, every direction is a direction of descent. In these places, right, this could be considered a maximum. This could be considered a minimum. Okay? Where this happens is where the gradient is 0. Right? And we have to be a little careful here. This happens when the gradient equals the vector 0, 0. Okay. Let's see why that is. Let's look at a fairly simple example where we could just tell right off the bat what's going on. If f of xy equals, let's just say, x squared plus y squared. Okay, that's a very standard paraboloid. All right, so here's the paraboloid. You could use whatever method you want to visualize this, either traces or level curves. Right? Either way, you're going to get a paraboloid opening upwards. We have a minimum here at the origin 0, 0. Okay, so if we find the gradient, all right, which will be the vector 2x comma 2y, the gradient at 0, 0 is the vector 0, 0, right? And this corresponds with the minimum. Okay? So it turns out that a critical point in 3 dimensions or on surfaces corresponds in the same way as it does in Cal 1. Instead of it being where the derivative equals 0, it's where the gradient equals 0. Okay, so put simply, the point AB is a critical point of the surface z equals f of x, y, if and only if the gradient of f at the point AB is 0. In other words, if f sub x comma f sub y, if that vector at the point, let me write it like this, at the point AB is the vector 0, 0. In other words, if f sub x at AB is equal to 0 and f sub y at AB is equal to 0. Okay? It has to cause both to happen. And as we'll see in the next examples, there are situations, there are curves along which, say, f sub x will be 0, and curves where f sub y will be 0, but we have to find the points where both are 0 simultaneously. All right, so that's an important distinction. Both must be 0 simultaneously. Okay, so how I like to break this up is I like to look at 2 examples specifically, and first just find the critical points. Then I like to go back and look at the same examples and then classify those critical points as maxes and mins. Okay, that's how I like to split up this particular section. Okay, so first we're going to look at examples of finding critical points. Then we're going to talk about how we establish whether they're maxes or mins or neither, and then we'll look at the same examples again. All right, so let's jump to those examples. All right, so let's find all the critical points of f of xy equals 4 plus x cubed plus y cubed minus 3xy. Okay, so this is basically going to be involving finding the gradient and setting it equal to 0. And what I want to really show is, like, there are way more cases than I could ever show, but most of what you'll see will fall into 2 categories when we go to solve for critical points. Okay, so let's start here. So what we want to do is find f sub x and f sub y. Okay, so f sub x is going to be 3x squared minus 3y. Okay, when we differentiate, and then f sub y is going to be, well, the 4 goes away, the x cubed goes away, we'll get 3y squared minus 3x. All right, and our first step here is to set these both equal to 0. Okay, now how I typically like to do this, okay, is I like to label these as, say, equation 1 and equation 2. So the process for finding critical points usually follows this method, right? Is solve one equation as far as you can. Okay. 2. Take the result from this first part and plug it into the second equation. Okay. And then 3, solve everything that's left, right? I'll just say finish solving. And this will make more sense when you see it in action. Okay, so I'm going to start with equation 1 and start to solve it, right? So equation 1 is 3x squared minus 3y is equal to 0. Okay, well, the best I can do is maybe move the 3y over to get 3x squared is equal to 3y. And divide through by the 3's, and we get y is equal to x squared. Okay, that's what I mean is solve one equation as far as you can. We're not going to get numbers out here. Sometimes you will, sometimes you won't. Okay, so here we didn't get any numbers. We just got, we got a curve, y equals x squared. So now we're going to plug, say take what you got in the last step and plug it into the other equation. So our other equation, equation 2, was 3y squared minus 3x equals 0. So I'm going to take this, y equals x squared. So y is equal to x squared, so I'm going to take that x squared and plug it into y. Okay, which is going to change this to 3, the y becomes x squared, but we're squaring y, so it's going to be 3 times x squared squared minus 3x equals 0. Okay, so we're going to get 3x to the 4th minus 3x is equal to 0. And now we can continue solving, and that's where we get to here. Finish solving. All right, so now I will say factor out of 3x to get 3x times x cubed minus 1 equals 0. So now I have that x is equal to 0, or here x cubed is equal to 1, which tells me that x is equal to 1. We're not quite done yet. All right, we have our x values. We need to plug them back in to get our y values. So now we plug them back into here. All right, so if y is equal to x squared, and we get that x is 0 or 1, this tells us that our critical points are, let me write it here, x equals 0, y equals 0, or x equals 1, y equals 1. So we get the points 0, 0, or 1, 1. Okay? So these are the critical points. 0, 0, and 1, 1. Okay, so what I want to show, though, is, well, first of all, if we go back up here to what our derivatives are, if you plug in 0, 0 and 1, 1, in doing that, both of these will come out to be 0. Okay? So that's one thing to check. Okay. What I want to mention is when we solved this, right, this was f sub x equals 0. So when we got to here, the y equals x squared, well, y equals x squared is a parabola. Okay, so I'm going to put it in blue here. So when we solved f sub x equals 0, we got this curve y equals x squared. Okay, now for the record, it does not actually matter which of these equations you solve first. All right, so along this entire curve, f sub x is 0. Now, if we were to solve f sub y equals to 0 first, right, we have 3y squared minus 3x is equal to 0. We'll get 3y squared is equal to 3x, so we get x is equal to y squared. So you can either remember that that's a sideways parabola or solve it to get that y is equal to plus or minus the square root of x, and we get this. So this is when f sub y is equal to 0 along the sideways parabola x equals y squared. And where these two intersect are where the gradient equals 0. Okay, so that's what we are trying to find when we're finding the critical points, right? We get a critical point at 0, 0 and at 1, 1. All right, let's look at this next example. We want to find all the critical points of the surface f of xy equals 3x squared y plus y cubed minus 3x squared minus 3y squared plus 2. All right, so the first step is what it's always been when we try and find critical points. We set the gradient equal to 0. Something interesting actually about the gradient is in other countries, they often call slope a gradient anyway. So in those countries, this is still just called the multidimensional gradient, right? Because it works in much the same way. All right, anyway, that essentially means we're taking f sub x and f sub y and setting them both equal to 0 simultaneously. All right. So let's do that. F sub x is going to be, well, when we go through and differentiate this, we're going to get 6xy. The y cubed goes away, and we'll get minus 6x. The minus 3y squared goes away, and the plus 2 goes away. All right, so there's our f sub x. I'm going to set that equal to 0. And our f sub y. All right, so our f sub y, we're going to get 3x squared plus 3y squared. Okay, this will go away, and then we'll get minus 6y, and the plus 2 will go away. All right, we're going to set that equal to 0. Now, as I mentioned, I just label these 1 and 2. And as I said, it doesn't really matter which one you solve first. Okay, this one, I think solving 1 would be a lot easier, so that's what I'm going to do. I'm going to solve 1. So first, I'll divide by 6 to get that 6y minus x is equal to 0. And then, here's the other type of situation we might have. Is something like this. If I factor out x, I'll get x times y minus 1 equals 0. Okay? So last time, remember, we actually got a curve out, like a y equals something in terms of x. In this case, what we got instead was x equals 0 or y equals 1. Right? This gives us two cases that we need to check. Right, we're still going to plug both of these into equation 2, but we just have two things that we have to do that with. Right, I'm going to plug in x equals 0 and y equals 0. Whoops, not 0, sorry. Y equals 1. Okay, so when x equals 0, equation 2 becomes, I'm going to write it in, let's do it in red. Okay, when x is 0, that piece goes to 0, so we'll get 3 times 0 squared plus 3y squared minus 6y equals 0. So this goes away, and now we have 3y squared minus 6y is equal to 0. I'll go ahead and divide by 3 to get y squared minus 2y is equal to 0. Okay, then we factor out a y. So y is equal to 0, or y is equal to 2. Okay, so the x equals 0 case gave us y equals 0 or y equals 2. So this implies that our critical points in this case are 0, 0 and 0, 2. All right, we got both of these points from here. All right, for the next case, when y equals 1, 2 becomes, well, when y equals 1, I'm going to replace all my y's with 1. So let me use, I'll do this one in pink. All right, the 3x squared is going to stay the same. Okay, then we'll get plus 3 times 1 squared minus 6 times 1 equals 0. Okay, so we get 3x squared minus 3 equals 0. Dividing by 3, we'll get x squared minus 1. So x squared is equal to 1, which means that x is plus or minus 1. Okay, so the y equals 1 case gave us x is either positive or negative 1. So this gave us critical points. Now remember, careful here, 1, 1 and negative 1, 1. Okay, so our critical points are all 4 of these. Now I do want to show what happened here when we did this. So when we solved for f sub x equals 0, it gave us x equals 0 and y equals 1. So if we go to the graph, all right, x equals 0, well, x equals 0 is this vertical line here. That's actually the y-axis. Okay, so that's x equals 0. And y equals 1, we'll put that here. That's this horizontal line. So that's y equals 1. Okay, so now this little cross I just made, this is where f sub x equals 0. Now, don't think that 0, 1 is a critical point. Okay, it's not. It's this intersection here is only where f sub x equals 0. Okay, if we instead had solved f sub y equals 0, okay, so f sub y equals 0 is a tougher one to solve. So f sub y, okay, rewritten here, if I go ahead and divide by 3, just to simplify it, okay, this is almost like a circle. Okay, in fact, so here I have y squared minus 3y. If I were to, sorry, my bad, that's a 2y. Okay, if I were to add a 1 on both sides, this would actually factor. This would be x squared plus y minus 1 all squared equals 1. This is the circle of radius 1 centered at the point 0, 1. So 0, 1, oh, that's the center, and we have radius 1. So this circle is where, in blue here, of course I can't draw worth a damn, this blue here is where our f sub y equals 0. And where this cross intersects with the circle, that's where our critical points are. At 0, 0, at 1, 1, at 0, 2, and at negative 1, 1. Okay, so that's essentially what we're finding, is where the curves along which the partial derivatives are 0 intersect. So that at these yellow points here are where the gradient is equal to 0, where both are equal to 0 simultaneously. All right, so now that we've done some examples of finding critical points, and as I said, there are a myriad of possibilities, but they all sort of follow that same idea. You're either going to get a curve that you plug into the other equation, or you're going to get cases that you're going to plug into the other equation, and you just keep solving till you get everything. You just got to be careful. Okay, once we have the critical points, then the question becomes, well, how do we classify them? All right, so here's how we classify them. It's similar to one of the methods we had in Calculus 2. So, or not Calculus 2, but Calculus 1. So in Calculus 1, we had basically two possibilities. We had the first derivative test and the second derivative test. Okay? And the first derivative test, you would find your critical points, and then you would make a number line, like maybe you had first critical point, second critical point, third critical point, and you would check the derivative to see in the regions in between whether it was positive or negative or positive, right? So wherever it would change from, say, positive to negative, f would be changing from increasing to decreasing, so you would know that you had a max. Okay, if it changed from decreasing to increasing, you'd know that you had a min. And if it, say, went from decreasing to decreasing or increasing to increasing, you knew you had, well, neither. Okay, this is probably an inflection point. All right, and I find whenever I teach Calculus 1 that students tend to prefer this method, and that's perfectly fine. It's actually a pretty good method for the most part. It will always work, and you know, you don't have to take another derivative. However, it's not going to move to Calculus 3. Okay, so this won't move further, because when you find a critical point for a surface, it's not as simple as just checking to the left and the right. Yes, you can check from the left and the right, but also from the top and the bottom, from the diagonals, right? The 45 degrees, 30 degrees, right? There are too many directions to check, right? We can't check every direction anymore. Okay, so that leads us with the second derivative test. Well, the second derivative test, that instead looked at the second derivative at the critical points. Right, because if at a critical point, say f double prime was negative, that would mean f was concave down, and concave down at a critical point meant that we had a maximum. Okay, and if f double prime was positive at the critical point, that would mean f was concave up, which would mean we had a minimum. Okay, now this was great, except it doesn't always work, because if f double prime is 0, then it's inconclusive. Right, we have no idea what's going on. It could be anything. We'd have to check something else. because it could just be, it could be a max that just has a really wide base like that, or it could be an inflection point. Okay, quite a few things could be happening there. It could also just, it could just be a place where, say, the function is linear there. Okay, so actually it'd be more like this. It'd be linear there. Okay, so in my experience, I actually prefer the second derivative test. However, the problem is it doesn't always work, and sometimes it's a pain because you have to take another derivative. So it turns out that this is what will move further. Okay, but there's some complications that arise from the fact that, well, we're talking about multiple dimensions. All right, so let's talk about now the second derivative test for surfaces. Okay, so this is quite a bit to take in, but let's suppose that AB is a critical point of f of xy, and the second order partial derivatives of f are continuous in a region containing AB. So basically, we have a critical point, and then all the partial derivatives and second order derivatives are nice and continuous and yada, yada, yada. Now, here's the important part. We're going to create this new function, call it capital D, d of xy, which is f sub xx times f sub yy minus f sub xy all squared. Okay, well, I'm going to talk a little bit about this in a minute, but this is basically, you can think of it as a testing function. It basically tells you whether or not everything is behaving the same in all directions or whether it's not. Okay? So, if the testing function at AB is positive, then, AB is a local extrema, right? So this is the testing function, right? If D is positive, then we have a local extrema. Then we just step back to what we know from before and see whether it's a max or a min. Okay, so if the second derivative is negative, right, that means we're concave down. So that means we have a maximum. And notice you can check f sub xx or f sub yy. Right? So either direction, in the x direction or the y direction. If on the other hand the second derivatives are positive, either f sub xx or f sub yy, then you have a minimum because that means that they are concave down. All right, so, or sorry, concave up. So here we have concave down, here we have concave up. Okay, the next case, if our testing function D is negative, then AB is a saddle point. Well, what's a saddle point? Well, saddle point is, that's basically our neither case, right? That means we have a max in one direction and a min in the other. Right, so we kind of looked at that situation in an earlier video. And I think I mentioned then that it was a saddle point. We have something like this happening. So D is actually testing whether something like this happens. So D is the saddle point test. Okay, now there's a lot to what this thing is. If you've taken some linear algebra, you may have seen this before. This is a pretty advanced function here. I don't want you to worry too much about where it comes from or what it really is. We could spend days talking about it. The intuitive thing, though, okay, is if fxx and fyy have the same term, or sorry, have the same sign, right? If they're both positive or both negative, then this is going to be positive. Okay? However, if they have different signs, this will be negative, and then we're subtracting another negative, right? Because this thing is squared, so this will always be subtracting something away that's positive or 0. If these have opposite signs, this whole thing is definitely going to be negative. Okay, again, like I said, there's more to it than that, but this is basically checking, do fxx and fyy have the same sign? Now, there's more to it than that, because they could have the same sign, but we could still have a saddle point. One of them could be 0, right? There's more to it than that, but that's the intuitive idea. Okay, this is the saddle point test. If capital D is negative, you have a saddle point. If it's positive, then it's a max or a min. Then you just check to see which one it is. And then third case, which is just like in Cal 1, if D, AB equals 0, then the test is inconclusive. All right, so you'll have to do something else to figure out what's going on at that critical point. Okay, so I think it's better to see this stuff in action. So let's go back to the examples we looked at where we already have the critical points, and then we will apply the second derivative test, and then we'll take a look at the graph. All right, so back to that first example we looked at, which was 4 plus x cubed plus y cubed minus 3xy. We already found the partial derivatives, 3x squared minus 3y, and f sub y equal to 3y squared minus 3x. And the critical points we found were 0, 0, and 1, 1. Okay, so to find whether these are maxes or mins, using the second derivative test, well, we need to find all of the second derivatives. So we need all of the second derivatives. Okay, so we'll just go through it. We need f sub xx, so we'll take the derivative of f sub x with respect to x. So we'll get 6x. We need f sub yy. Well, that will be 6y. Okay, and then we need f sub xy. All right, so f sub xy, you can either do the x derivative of f sub y or the y derivative of f sub x. Doesn't matter. Either way you go, you should get -3. Now, you might think that, oh, look how similar these are. That means they have the same sign. Not exactly, right? If you're in quadrant 2, this would be this would be negative and this would be positive, right? So there's way more to it than just seeing if these kind of line up. That's why we need the testing function. So our testing function D is fxx times fyy minus fxy squared. Now, if you have trouble remembering this, just remember that it takes care of all the possibilities. It doesn't quite look like it here, but we have this second derivative, so the matching ones, and then this is actually f sub xy times f sub yx. It's the other two possibilities, but as we talked about in the last video, since those are the same, it comes out to be that squared. Okay, so when we simplify or plug all this stuff in, we get 6x times 6y, so 36xy minus a -3 squared. So it would be 36xy minus 9. Okay, so there we go. Now we're going to start classifying these critical points. All right, so we're just going to go through it. At 0, 0, we first always check D. Okay, so D at 0, 0, this piece disappears, and then we get 0 minus 9, which is negative. So 0, 0 is the saddle point. And we can stop there. Okay? And then we'll check 1, 1. All right, 1, 1. Well, when we plug in 1, 1, we'll get 36 minus 9. That will be positive. So that means that we have an extreme, right? A max or a min. And we check that using either fxx or fyy. It's not going to matter. Either one of them are going to give us 6, which will be positive, which means that we're concave up. That means we're making a U. That means we have a minimum at 1, 1. Okay, so let's look on a graph and see what we get. All right, so here's a picture of the surface. I've kind of zoomed in close by. And we see here over 1, 1, this is point 1, 1, 0. Right above it, we see we have a minimum. And it even kind of shows us what's going on in one direction. We have a minimum here. In another direction, we have a minimum. Okay, concave up, right, which aligns with what we see here. And then over the origin, right, 0, 0, we see you can almost see it right here, we have some weirdness going on here where it's actually, it's not even a max in one direction and a min in another. It looks like an inflection point in one direction and an inflection point in the other direction. Okay, so that is what the, but at the same time, when I look at it this way, you see I see a min in this direction, and if I look at it, you can kind of see it through there. I see a min in this direction and a max in this direction, right? So at some direction, within some direction, there is a max in one direction and a min in the other, right? So it might not be along the x and the y direction. It could be along other directions, but that's what that D function checks for us. Okay, so there we go on the graph. All right, so let's look at the other example, and that should do it for this particular lecture. Okay, so that second example we looked at, we've already found f sub x, f sub y, and the critical points 0, 0, 0, 2, 1, 1, and negative 1, 1. Okay, so now we need to find the other partial, or not the other, but the second partial derivatives. All right, so we'll just crank through that. F sub xx, we're going to differentiate this with respect to x, so we'll get 6y minus 6. Okay, f sub yy, again, we differentiate this with respect to y, so the 3x squared disappears. We'll get 6y minus 6. Once again, we get the same looking thing here. In fact, we get the exact same thing. That's not always going to be the case. All right, just for the record. And then f sub xy. Now, I could take either, I'm probably going to start here. F sub x with respect to y will be 6x, and the minus 6x will disappear. Okay. Then from here, we can make our D, which remember was f sub xx times f sub yy minus f sub xy squared. Okay, so it's going to be these two things multiplied together. Since it's the same thing, that will be 6y minus 6 squared. Okay, then minus this squared, which will be 6x all squared. So our D I will simplify as, I'm going to go ahead and factor out the 6 there to get 36 times y minus 1 all squared minus 36, oops, 36x squared. Okay, which we could rewrite now as 36 times y minus 1 all squared minus x squared. We don't have to do this, but it might make things easier to figure out whether this is positive or negative, because the 36 isn't going to affect it at all. It's really just this that's going to affect it. Okay, so now we're just going to go through each critical point and see what we get. So for 0, 0, d of 0, 0 is going to be 36 times, that will be negative 1 squared, so 1 minus 0. So that's going to be positive. So that means we have a max or a min. So now we just need to figure out which one it is. And we can, well, as we can see here, it doesn't matter which one we use literally here since they're the same. So f sub xx at 0, 0 is going to be 0 minus 6, which is negative. So negative means concave down. Concave down means that, which means we have a max. So we have a max at 0, 0. Okay. Then at 0, 2, so d at 0, 2, so that'll be 36 times, when we plug in the 2, we still get 1 there, so it'll be 1 minus 0, so that's positive. So that's a max or a min. Okay, so let's check it at f sub xx. When we plug in 0, 2, we'll get, when we plug in 2 into our y, we'll get 12 minus 6, that's positive. So that's concave up, which is a u, which is a minimum. You see what I'm doing here, where I'm saying at each step what it is? I don't feel like you have to say positive and just know it's minimum. There's a reason, right? There's a logical process. So if it takes this to get you there, that's really no problem. Okay? Now, 1, 1. So d of 1, 1, well, when I plug that in for 36, that makes the y piece 0. So it'll be 0 minus 1. So that's going to be a negative 36. So that's a saddle point. And then at negative 1, 1, right, we'll get 36 times the 1 makes that 0 again. The negative 1 squared is still 1. So again, we get negative, which will be a saddle point. So if I go back to this little graph I drew earlier, okay, what we basically have found is we had a max here at 0, 0, a minimum here at 0, 2, and these were saddle points. Okay, so let's take a look at the graph and see if that aligns with what we have. All right, so here's the surface. And as we can see, above 0, 0 here, we have a maximum. Below 0, 2, we have the minimum. And then at the 1, 1 and negative 1, 1, we have our saddle points. So it's, again, it can be kind of tough to see what's going on with the saddle points. But here, if I look at this one, in this direction here, we see a minimum, but then if I spin around this way, we see that there's a maximum there. right? So that's what that D function is testing. Here, on this other saddle point, as we see in this particular direction, looking at it this way, we see that we have a minimum, and if we spin around this way, we have what looks like a maximum there. Okay, now these can be tough to find just on your own, just looking at a graph. So that is part of the reason why we need this analytical tool of using the second derivative test. All right. All right, so that should about do it for this particular lecture. In the next one, we're going to look at how we tackle absolute maxes and mins with constraints, right? Constraining surfaces over, say, a circle or just over a particular line. All right, so I will talk to you